Good day, welcome to lesson 7. Today's topic we will be looking at spatial data input and collection. So firstly, we have talked briefly in previous lessons about various sources of GIS data input. And we're just going to recap some of that briefly here. So for example, we know that we can actually source various forms of digital data. For example, we have our vector data, or example shape files that we use in ArcGIS. Remember, the shape file is an example of a standard data format, map data format for GIS data. Then we also have other examples of digital forms of GIS data, such as raster data models that we can acquire from satellite imagery, aerial photos, etc. Data can also be brought in from various types of databases, including Excel spreadsheets. All of you all should be familiar with the Excel spreadsheets. And then of course we can also have digital data in the form of survey data. For example, survey data such as engineering survey data. Every time I say engineering survey data, please be aware that I am talking about the kind of data that is collected when surveyors go out into the field to conduct their measurements of the landscape. Then we also have various forms of non-digital graphics, and these would include paper maps. For example, we talked about various types of paper maps in one of our early lessons. Photographs of all kinds, sketches, diagrams, etc. Now remember, when we have non-digital forms of data that we want to put into GIS, it usually requires converting it into a digital format, such as scanning or digitizing, for example. We can also include scientific reports, a report in the form of a Word document, for example, and this will require hyperlinking the documents from its location on, let's say, for example, your hard drive, hyperlinking it to a map feature in ArcGIS, for example. Alright, so usually when you go into your map, if you click on the feature, the document will pop up for you to have access. Okay, and the last point is really just a reminder to you that when it comes to data input and collection in any GIS, remember this is a critical step in the development of any GIS. This represents between 60 to 80% of all cost and time. So this is the most cost intensive, time intensive phase of the development of any GIS. Okay. Alright, now let us look at how we can acquire data, specifically geometric data. And again, when we talk about geometric data, I'm referring specifically to the map. Remember, the map would be made up of features that display or represent shapes, sizes, location, etc. So when we talk about geometry or geometric data, we are talking about the map data. So how can we acquire map data as well as attribute data? Firstly, we can do that directly. We can directly acquire data using land surveying methods or engineering surveying. For example, we can use, when the guys go out into the field to conduct their measurements of a landscape, they can use these instruments such as a total station. This is what it would look like. Here you have the tripods, you'll be familiar with that. Then there's a total station instrument mounted on top of it, and this instrument allows the surveyor to collect measurements of points, lines, and area features, just as we have them in GIS, but those measurements can actually be captured in a digital form that can actually go directly into your GIS database. So as indicated here, this type of data collection would actually directly produce vector data. We can also acquire vector data using photogrammetry, right? For here we said it, vector data can be measured using digital survey equipment such as the total station, as we have here, or an analytical photogrammetric plotter, such as we have this setup here. So what we have, this guy is sitting in a lab. He's sitting at there is a computer setup here, and there's another instrument attached to it. You see where he actually looks through this instrument. What he is seeing is there would be aerial photos, two overlapping aerial photos that would be mounted in such a way that he would be able to view those images in 3D from these lenses, and as a result he would actually be able to digitize features including elevation from that 3D view of the aerial photos. So this is the kind of data that photogrammetric stations or photogrammetric plotters would allow you to acquire. Right, then of course we have raster data that are sometimes obtained from remote sensing data. Remember, remote sensing data would be satellite imagery and also aerial photos. And then we acquire data from digitizing existing maps as well. So I would have described this process to you in a previous lesson, where you can have your paper maps which would be mounted on a tablet digitizer, that's electronic table, where you would trace the features on the paper map using the digitizer instrument. You can also digitize the existing maps by scanning it. When you scan it, it's converted into a digital format. So scanning, unlike the previous methods we just looked at in the previous slide, scanning produces raster data, whereas vector data is produced by digitizing. Okay, so you need to remember that's an important point there. Raster produces scanning produces raster data, vector produces digitizing produces vector data, and scanning produces raster data. And oftentimes in GIS you find that as you have to work with these data sets, you may have to convert back and forth between one data model and another, such as from raster to vector or vector to raster. But please be aware that when you make this conversion, there is automatically an inherent amount of data error that would be propagated when you each time you make a conversion. And this is an issue I would have mentioned to you previously as well. Okay, so methods of producing digital maps, right? So we're recapping a little bit. So we have digitizing existing maps using the digitizer, such as a tablet digitizer. We can scan the maps as well. All of this is converting the data into a digital format. We can collect data as well by photogrammetric map production methods. Remember, that was a method where the guy was sitting at in a computer lab looking through some lenses at some 3D images. Digital data, sorry, can also be captured from computing coordinates from field measurements, such as if you go out into the field with your handheld GPS equipment or your phone, as the case may be. Also, data can come to us in the form of Excel spreadsheets, where the data would be contained within the cells of a spreadsheet, and that can then be converted into map data. For example, you can actually input GPS coordinates in that spreadsheet and automatically convert that to point features in your ArcGIS. So here we have some charts that I want to spend just a little bit of time looking at that summarizes some of these issues for us very nicely. So in the left chart here, what we're really doing is looking at a comparison between the traditional paper method and the GIS mapping. So with the traditional method, we know that when we collect our data, whether it is in the form of aerial photos, etc., usually to create the map it would have been back-breaking work. You see the pencil and the markers and etc. to create that map. Once that map has been created, a map is usually created in order to extract information. So what would normally have happened is that you would have to use your magnifying glass and what have you in order to actually see what's going on there. Then you'll have to use instruments such as compass, calculator, etc. to actually derive information such as distances, areas, etc. Now you all have had experience in the lab, so you would have been able to see some examples of how some of this is done in ArcGIS, and everything is automated for you in a digital environment. For example, we can very easily perform spatial queries as well as attribute queries. Spatial queries, remember, would be on a map. Attribute queries would be from the table. You can carry out spatial analysis. For example, you can automatically create buffers around a point. So all of this can be done very easily in a GIS environment. But remember, the point here is, as I made in a previous slide, is that 60 to 80% of the time is spent in collecting and inputting that data. Cost is it's a very expensive, very labor intensive stage of the project. But once the data is available and accurate data is available, it's very easy for you to utilize the data at that point. Now over in this chart we have a summary of what we were talking about in terms of data acquisition and data collection methods. So remember, we start at the beginning where we have data from such as remote sensing methods, satellites, imagery, or aerial photos. Once the data is collected, we need to convert that into a digital format. For example, you see the picture of the guy here, he's digitizing the map. Over here the alternative is to scan it. Remember, when we digitizing produces vector data, scanning produces raster data. We can convert back and forth between the two. Once that is done, we have to make sure that we make time for editing errors out of the data before we can actually perform analysis. Alright, and in terms of editing data, editing errors, here we see ground surveying data can be used to actually correct data, because remember, ground survey data would tend to be of highest accuracy that you can find. Right, so continuing, sorry. So if you recall, digitizing, this is a process by which map coordinates, images, or other sources are converted into a digital form for your GIS. So we can digitize points, lines, and polygons that represent real-world entities, which can then be recorded in a digital format for you. So this is our definition here of digitizing. So we have three types of digitizing. We would have touched on two of them already. We have our manual map digitizing, which is human guided coordinate capture. That's where we're tracing the features on the map digitally. We can scan. So this is the scanning process is an optical scanning that converts hard copy documents into digital formats. And then the third format, which we have not addressed yet, this is called on-screen digitizing, and this is a combination of manual and scanning. So really how this works is you can be sitting at your computer in a computer lab. You will have a scanned image of an aerial photo on the screen, and you can, using the tools in ArcGIS, you'll be able to actually digitize vector features such as points, lines, or polygons off of that image. Here we can actually get some visuals of that. So here we have our manual digitizing. Here you see the digital table, the electronic table where the map has been mounted, and you see the guy leaning forward using the digitizing instrument to trace the features. Here we have our scan digitizing. So the lady is scanning a large map through a large size scanner. This is not your typical desktop scanner. And here's an example of on-screen digitizing, where you can clearly see the person is tracing polygon features over a map using the mouse. So let's look a bit more at the process of manual digitizing. So the digitizers, now remember, we have these the tablet, we have the electronic table that will be connected to a computer. The electronic table and the computer will have an internal coordinate system. So normally what we would be required to do is we would be required to cross-register that internal coordinate system with known coordinates. So we have to match the coordinates. Okay, and before we do that, normally what we would have to do is we would have to set what we call as tick boundaries. That would be the corners of the map. So those tick boundaries would have those internal coordinates, right? The computer internal coordinates. So here we have an example of what that looks like. So we have the ticks 1, 2, 3, 4 tick IDs, and these here, this X digitizer, Y digitizer, these would be your X and Y internal coordinates. So what we have to do now is, according to what we see on the map, the location of these points on the map, we have to match them to known coordinates. So some research will have to be done to identify the actual ground coordinates of those features on the maps, and then we can match it here. So we see all of this information is compiled in this registration table here, and once that is done, we can now actually register our paper map that has been mounted on our electronic table. We can now match that to real world coordinates. So once the digitizing begins, you will be digitizing in real geographic space. So when we digitize now, remember we are still utilizing the digitizing tablet. We have two methods that can be used. We have what we call the point digitizing and stream digitizing. So the point digitizing, this is where crosshairs is placed over the position, such as a point or a line, and is recorded at the location by pressing a key. This is best used for straight line segments such as property boundaries. The stream digitizing, you're using a similar method, except it's not straight lines. It's actually you're using sinuous lines or curved lines, such as contours or soil boundaries. Okay, and this is recorded at very short preset individuals. So as you're digitizing, the intervals are so tiny that it actually allows you to create continuous lines. However, please note that the point digitizing method tends to be considered of greater accuracy than the stream digitizing, because as you could imagine, if digitizing continuous curving lines, you're more likely to make mistakes with your hand shifting. So what are some of the errors associated with digitizing? We have crossing contour lines. So I mean, I don't think that needs any explanation. Contour lines that would cross each other, touch each other, you know that shouldn't be happening, right? Then you have gaps between lines that should not have gaps. You have lines crossing over each other where they should meet, they don't meet. Lines meeting at the wrong points. So for a visual of what we're talking about, let's go to the next slide. So these are examples of digitizing errors. Let's look at this here. This is an example of some digitizing errors, and this is what it should look like had it been correct. Now the broken circles around the points refers to what we call snap tolerance. So that really is a setting in the GIS software that can be set beforehand that says if my endpoint comes within a certain distance of another endpoint, automatically snap. So that makes it easier to achieve accuracy. But here are some of the errors. Here we have undershoots. That means that these lines fell short of connecting with this line. Then we have two lines failing to meet where they should have met. Then we have an overshoot, which is the opposite of an undershoot, where the line went beyond where it was supposed to connect. This is what a correct version should look like. Okay, additionally on this side we see all of those: overshoot, undershoot. This one is a dangle node. That means that this one, it shouldn't be there at all. This segment of line shouldn't be there at all. Then we have missing label points. All right, because each feature will have a label or an ID. All right, pseudo nodes, this means that a node was included there when it should not have been there. So these are all various types of errors occurring, digitizing errors. So when we acquire or achieve these errors, how can we fix it? What can we do? So quality improvement, this is a necessary stage of the entire digitizing process. Remember I said that before. Once you've acquired your data, before you begin analysis, you must carry out or conduct error correction. Okay, so there should be error correction. Where you have missing data, you need to make sure you include missing data, such as those missing label points or missing attribute information. So as we had seen in the previous slides, many of the types of errors we looked at, digitizing errors, would have been examples of topological errors. So where you have topological errors, you will have to fix those. For example, in ArcGIS, we have tools that allow us to actually carry out automatic topological checks. So it's not necessarily fixing it for you, but it's identifying where you have one. So this here is a print screen or screen grab of an example of the results of where that topological check had been carried out. And here you can see in the red area, this is where you have an overlap between the two polygons where there should not be an overlap. So that error would need to be corrected. Now, scan digitizing. So when we're performing scan digitizing, we're actually carrying out two operations at the same time. We are scanning, that is, we're capturing the reflectance differences in what is seen, what the sensors see, and then as we scan, we carry out binary encoding. So scanning involves passing of a sensing element over the map, which measures both the precise location of the points and the strength of the light reflected. So it's capturing two sets of information: the location and the strength of the light reflected. Okay, so once that information is collected, now it has to be given a value, it has to be given relevance. So that's where the encoding comes in. So the reflectance values are converted to numbers within the pixels, and that is what we call encoding. So you all should understand this principle by now, because remember, when scanning produces raster data, and when we have raster data, remember each one of those cells must be encoded with a value. Alright, and then again, as mentioned earlier, vectorization would be the process of converting from raster to vector or vector to raster. And this must be part of the editing process as well, or this is part of the editing process. And the result of vectorization is a continuous feature delineated by a sequence of coordinates that represent the midline of the feature. So for example, remember with raster data, each cell has a resolution, or it has a dimension. So if you have to convert that raster data format into a vector, you need to, the system is going to make a determination as to where to draw that line, where to place that point, and it will choose a midpoint of the cells in order to make that to create that feature. So this is what that point means. So now we want to very briefly compare manual digitizing with scanning. So what are the advantages of manual digitizing? Manual digitizing is performed using relatively inexpensive equipment. It's not as expensive as having to acquire data from satellites or to get those huge industrial size scanning equipment. It also requires little training. For example, somebody could be trained to use those digitizing electronic digitizing tablet probably in a couple hours, and they can be ready to get going. Doesn't mean they would necessarily have a high level of accuracy, but they would be able to actually produce something. Manual digitizing, usually as well, high map quality is not required, because remember, there's a lot of human involvement there, so the probability of error is relatively high. Okay, and generally further editing may be unnecessary as long as you don't really mess things up in a bad way. Their disadvantages, on the other hand, is very tedious, as you could and time consuming. So if you recall the photo of the guy actually leaning over the digitizing tablet, if you have a lot of work on a very complicated map to digitize, as you can imagine, that is going to be very time consuming and back-breaking work. It's not easy at all. So that is a major drawback to the use of manual digitizing. Now with regards to scanning, we know that scanning can be easily performed. Once you have the equipment, you program the requirements of the operation that needs to be carried out, you feed in your map, it automatically scans and rapidly compiles digital images for you. So it can be done very quickly. The disadvantage of scanning, however, is that, as we would have said before, raster data produces large files that take up a lot of space compared to vector. Also, the raster data, remember, it doesn't have an attribute table the way in which a vector data layer would have. So that means then that the data is not directly linked to lines and polygons. Remember, the cells would be encoded with values that would then have to be interpreted by someone who would have to define what those values mean for you. Improvement in data quality is also time consuming. So if there are errors in the values of any of those cells, someone trained and specialized in not only remote sensing technology, but someone who is an expert in a data type, for example, if it is forest cover, etc., this expert, or what we call a remote sensing specialist, they will have to make a determination and get involved in correcting the data. It's also relatively expensive equipment that are used with regards to scanning, and as I mentioned just above there, that it requires persons with certain expertise. For example, a photogrammetrist, again that was from earlier in today's lesson, or remote sensing specialist. So the remote sensing specialist, this person would not only be trained and expert in terms of the technical aspects of remote sensing, but they would also be very knowledgeable and highly trained in the particular data set, the particular data discipline, such as forestry, agriculture, oceanography, etc. Okay, so at this point I'd like to thank you for joining me for today's lesson, and I would like for you to proceed to eClassroom for the activity, the marked activity. Thank you for your cooperation.